Okay, welcome back. What I want to talk about today is really the strength of materials, and I'm in the lecture. I'm not going to try to get too deep, but I am going to try to give you some resources that can take you really deep if you want to. And this really title we'll call this the strength of materials. Really, this has to do with the structural properties of materials, and we could really do this in a lot of ways, but structural properties, strength, breaking, bending, all these are things that are very intuitively easy to understand, I believe. And I want to put a little bit of science behind that, and hopefully there's a way here where you can get your students to appreciate how science really applies to the real world. And that's, I think, what good science teaching is all about, seeing how these relationships happen between what we put into numbers and how this creates real meaning in the world. And I think mechanical behavior of materials is actually a really good way to do that. And maybe you'll agree, maybe not, but I think, again, this builds on a lot of the content that's already in the ASM camps. And I want to take you a little bit deeper and show you how that how macroscopic can go down and apply to the atomistic scale in this. So again, what we're going to do here is we're going to use structural materials as a present example. Again, material science is really all about this relationship between processing, giving you structure, giving you properties, and what we're going to be doing here is talking about mechanical properties. P-R-O-P-E-R-T. Mechanical properties, but we could really use other properties like electrical properties, catalytic properties, biological response of something. But mechanical properties, I contend, are something that everybody has some hands-on feeling with, and as a result of that, it's something you can get into intuitively and extend this possibly later on. You're more like graduate work probably. So this is structural properties are really easier to make all this stuff tangible, I believe, anyway. So that's why we'll focus on this. That's what we'll use in this course. So out of this lecture and the exam that follows, there's really three ways we can define the strength of a material. And strength, we mean can resist physical, mechanical loads on it. And there's resistance to elastic deformation. This means is something stiff enough? Is it going to deform? Is it going to be too floppy? Or is it going to be stiff enough? And this refers to basically reversible deformation. The other is going to be strong enough, and this is a resistance to plastic deformation. And here what we're talking about is permanent deformation. And then fracture is the other one. So you could see all of these things sort of in the context of something simple like a paper clip. I can take a paper clip and I can bend it, and if I don't push it too hard, it might be, if the wire is very thick, it might be very stiff. If it's very fine wire, if it might be made out of plastic, it might be very compliant. If it keeps snapping back to its original position, that's what we call elastic deformation. If we bend it too far and it doesn't come back, that's what we call plastic deformation. Those are two completely different definitions of strength. And then the last one you're all familiar with is if you take some things and you push on them too hard, they're just plain going to break, and that's fracture. And the important thing here is these all have different rules that govern the behavior. And so we can, as engineers, write these into quantitative rules, and those quantitative rules are different in all three of these cases. And we're not going to get into any depth, but I do want to get the idea of elastic is different than plastic is different than fracture. And then the other thing to appreciate any of this, and if we are going to be quantitative about it, and that's what we try to do at the university level anyway, we have to give real physical meaning to stress and strain, because that's the language we use to be quantitative about any of this. Okay, so let's go forward. I want to put this in the context of the 794 class, and what we're going to do is develop some goals that build on what we do later. So this stuff might seem a little bit abstract right now, and yeah, it is possibly, but bear with me, because what we're going to do later on is we're going to consider how we can tailor microstructure to give us resistance to plastic deformation. That is, how do we make strong materials? And that's really an interesting topic. do we make materials strong? And that will be one of the upcoming lectures. The other, I'm going to put this into the context of how we make an automobile body, and it's something, again, everybody can relate to. There's a lot of demands you put on an automobile body. If you want to do something like a Porsche or a Ferrari, it's got to be really stiff in order to give you good performance. That's not quite as important for a getting to the grocery store kind of car. But even for a getting to the grocery store car, you care that it's crash worthy. That is, it protects the occupants inside if there's a crash. There's a lot of materials properties that go into that. We also have to have things that are affordable, so manufacturing processes get into that. And we also have to have something that is going to last a long time. So things like corrosion and fracture and fatigue and all these ways things can degrade go into it. So actually, something like a vehicle body, and could apply to a bicycle or an airplane just as well, but I think we'll use the context of a automobile, brings together a lot of these things, and you can see exactly how the science folds into that. And later on, we'll do another lecture to see how all of this fits together in the context of sustainability. And one really interesting thing is that if you make a car lighter and lighter, of course, it'll probably burn less fuel, but it also becomes fairly expensive. And we'll try to put all of that into a context of sustainability and see how engineering really does treat sustainability in a very first order way. Okay, so again, in terms of the goals I have here, okay, let me one more slide before I get to that. Again, in the context of something like a vehicle, what we want to do is if you're going to make a bicycle, an automobile, or an airplane, you don't want to carry extra weight around. So any of these things, a goal is often to minimize the weight or mass of the body while meeting structural objectives. Structural objectives means it's stiff enough, it's not flimsy. If you have a shopping cart that bangs into it with a light dent or light force, it's not going to give you permanent deformation, doesn't dent easily, or it doesn't fracture. So failure modes include, again, excessive deformation. This is really resistance to elastic deformation. Permanent bending is resistance to plastic deformation. And then resistance to fracture is just fracture, or sometimes this is something we call toughness. And you'll see all of these words a little later in the lecture. Again, we'll go through that a little bit more carefully going forward. Okay, so my goals with this particular lecture are relatively modest. We could easily build this up. You could do actually several weeks probably on this topic and consider how to minimize weight and how to maximize robustness. And there's all kinds of things you could do that I really think are tangible for the students. And if anybody would like to develop something like that, I'd be very happy to get on the phone with you and discuss some ideas where you could do this with different kinds of metal. For example, just foreshadow this, you could consider aluminum versus steel. Aluminum has about 1/3 the density, also has about 1/3 the stiffness, but it turns out in bending that makes the aluminum behave much better than steel. And also aluminum is something you can buy very easily. If you go to McMaster Car, you can pick, for example, the thickness you want, you can pick the strength, and usually you can get it in like a full hard temper, and then you can see you can take a torch to it, make it very soft, and you'll see that the plastic properties change a lot and the elastic properties don't. But I think I'm getting kind of way ahead of myself, but I do want to foreshadow some of the things if you want further information where you can go. So if you do want further information, I'm going to take you through, I've got a couple things set up on my web browser here, but there are good links. The ASM Teacher's Handbook is outstanding. There's also a Pacific Northwest National Lab Handbook on composite beams. I'll show you where those are. There are two resources, or there's a great set of resources out of Cambridge University. This DOIT, the Dissemination of IT for the Promotion of Material Science out of Cambridge. I've got 2 full modules there I'll show you, and I'll show you a module on a tensile test as well. And then other things you could Google if you want to go further is stiffness and shape, section modulus and shape. And there's some really deep stuff. This would be kind of advanced at the high school, but I think it would actually fit in very, very well at a high school if you're talking about design or anything, or building mechanical stuff at all. There's a lot of great stuff that I think you can really get your hands around. And again, if anybody wants to do that, talk to me offline, and I'd be very happy to step you through that. So let's keep this, and I'm going to go to Firefox here. And what I'm going to go through here is, first of all, the ASM Materials Education Foundation. So let me just show you, if you put ASM Education Foundation into Google, the ASM Education Foundation pops right up. We can go there. And that should also pop right up. There we go. And if you go here, we can scroll down to educators, go to teachers resources, and there's some pretty good things here. Two in particular I'm going to point you towards. One is the STEM handbook. This is basically what you get at the teachers camp. It's available in digital form as well. How everyday things are made is a really good thing. Here's another one from Pacific Northwest National Lab that we'll show you in a second. Let's go to the STEM handbook first. What we can do, we can go to composites on this. Again, there's the same way this is done in the camps: solids, usually it's solids, metals, ceramics, polymers, composites is the way it's done. Go to composites, and in here there's a section here on how you make the strongest beam and elastic modulus, and this lecture today basically builds on that idea, that content. And that should be loading up any second now. Usually this is a good time to banter with a class. It doesn't work so well in distance. So, and so anyway, there's this attempt of how you can make the strongest beam, or this lab on how you can make the strongest beam. This is all written up already. Basically, you use something like this. I'll show this in a little bit. We can look at elastic deflection. Elastic deflection is, again, if you have a beam like this, how far will it deflect and recover? Plastic deformation would be if it doesn't recover. And we can go through that. And then also at the end of this, there's some stuff on stressed skin composites also that you can go through as well and do this. So this is pretty good. It doesn't give quite as much background as I will give, and there's actually a little bit better background given in this Pacific Northwest National Lab set of handouts. And if you go to, I believe it's section 8 in there, I just looked at this before this lecture. It's on composites. And what's nice about this, I think it does a little bit better job sometimes of integrating the theory into the experiments, although I think the other book does a better job of giving you experiments that are really much more practical for typical classes, because that was done more by high school teachers. This was done by lab guys. And I think you need input from both of these. So anyway, that's the preface. But if we go down here, look at the table of contents, the part that's important here probably is you go to composites. Stressed skin composites comes in here about 816, and we can go down and find that. Where are we at here? 7s. 8.3. Okay, so we can step more slowly through this. Kevlar laminating shows you how to laminate, make fiberglass, so on and so on. Here's stressed skin composites, and there is some teacher tips such that go with this. It shows you how to come up with what the stiffness is and so forth. It shows you what things look like before and after bending, how the strains develop as a result of this, and these show you basically the strains that develop. We'll talk about what strain is in a little bit in this lecture. And it takes you through a lab procedure where you can do this. And basically, this stiffness property that you get here is what we're really interested in when we talk about the stiffness of various materials. So And that takes you through this. And if you can set it up like this would really be a very good way to set this up where you've got a good clamp, and you could use a dial indicator to do this. If you've got still have anything like a machine shop in your school, they would have this, and this goes into airfoils after this. They would have this, but that dial indicator also, if you went to Harbor Freight, for example, I guess this is going to be hard to get exactly where I want, but if you go to Harbor Freight, for example, this dial indicator shows you how the beam deflects. Harbor Freight will fix you up with a dial indicator for cheap and get you something that's very very useful for that. You could measure deflection, for example. Okay, let me go back to the lecture and we'll run through this, and hopefully, I think I just continue recording. I believe everything is still there. So we can keep going with this, and oh, there's one more thing I want to show you before I get there. Keep sure continue recording. And then the last thing I wanted to show you in this was an example of a tensile test. And we do this all now. No, there's a couple more things I want to show you. So these are Cambridge University. This is their dissemination IT methods for promotion of material science, and they have these learning things here. That this is about mechanical testing, the mechanical behavior of materials, and typically what we do is we use tensile testing as kind of the gold standard. I'll talk a little bit about that in this lecture. Basically, what we do is we just put a force on this, pull this until this bends and either stretches and breaks. This is a neck in a bar, and eventually that breaks there. And if you go through this, there's a nice systematic approach that they go through. This talks about the aims, and you can see you can skip forward, and I will let you do that on your own time because and you can see there's a lot more depth here. This is tensile testing, shows you how you have an elastic range, a plastic range. We'll talk all about that. We talk some about beams in here. There's another learning module all about beams, and that's another good way of showing it. And again, the lab you saw there was about beams. So if you'd like to develop anything like this, again, I'd be very happy to talk you through it. And the last thing I wanted to show, and it's shown as into the PowerPoint also, is how tensile tests behave. And here's a YouTube that demonstrates that. This is 1018 steel. Again, you're using a force in the up and down direction that's stretching that bar. It's getting longer and longer, and this is force along this axis, elongation along that axis, and you can see you're starting to develop a neck right in that region. The beginning of the neck is always at the highest point of the curve, which is interesting. And again, load and elongation, you can see the amount of load it carries decreases, the amount of force it needs to stretch it is decreasing and decreasing as this neck forms, and eventually you're going to see it fail right near that neck. See the load decreasing, 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 and pretty soon that's just going to go pop and break right there. You see the load keeps dropping and dropping and dropping. Again, load on this axis, elongation on that axis, and there it is, it's broken. And so you finally went through fracture there. And again, lots and lots of great potential teaching stuff on YouTube. Okay, so let me go forward. And again, so this is a way you can do a lab like this. And again, what we're interested in is really reversible and irreversible deformation. Well, let's pick a better ink color. So elastic is reversible, and these equations here refer to the elastic regime. And what this tells you is again, you could do math with this. D is this deflection. F is equal to the force. L is equal to this length of the beam. E is equal to the elastic modulus. And I is something we call the moment of inertia, and it's just a geometric property here. You see it's B, which is this width. That should be a B. And then H is this thickness, as it's put here. You see the thickness is a third dependence. That's basically why aluminum actually acts a lot different than steel at the same weight, because it's a third the density. You get a much thicker beam out of aluminum than steel at the same weight. And then just a number 12. So you can predict all of this. If you make an aluminum or steel beam, you can make a very specific prediction of how much force will give you how much deflection. And you could do this with steel, aluminum, so forth, figure out the weight of it, try to figure out how to minimize the weight of a given beam. And it turns out that composites give you a much better way of doing that than monolithic materials, and shape makes a big deal. Tubes are better than rounds. But you can buy stuff like this if you go to McMaster.com. is a great place to buy shim stock, and you can buy various materials, aluminum, steel, stainless steel. Pick the thickness you want, and it's about 20 bucks or so for a nice roll of material where you know exactly what you have and exactly what the thickness is. So this is elastic. This is the reversible deformation here. And if I push too hard, if I push a little bit, you know it'll spring right back. If you push too hard, you get into plastic deformation. Then I'd continue to push, and it would stay, it wouldn't pop back, but it would remain with some permanent set, and would remain with particularly a bend in that region there. So a really nice slab you can do also is in the Materials Camp series. You've seen how materials can be work hardened, and you've also seen how they can be annealed. And if you did this, for example, with aluminum, and then you took it to a Bunsen burner or a propane torch, you could soften it, and you could see that for small loads, the elastic properties would be just about the same. The deflection you get at a given small load would be just about the same, but you'd find that the load that is required to give you a permanent deformation decreases dramatically if you end up heating this material up, annealing it. And so you can show that elastic properties and plastic properties are different. You can also show that there's different something that's governing it. You haven't changed the chemistry of the material. You've done something to it that's really softened it, and that begs the question, what have you done? And I'll start answering that, and then in another lecture we'll answer that in a little more depth. So okay, so elastic deformation, let me go back a little bit. This is done in bending. The other thing that we can do is we could do this on a regular stress strain curve like we talked about. And as you saw there in a second, this is kind of foreshadowing what we often see is an area that's really stiff, and then it starts to bend over here. And this real stiff area, this is the elastic part given by a modulus. And then you see some load which the material goes plastic, that it becomes irreversible. And if I were to unload, you'd unload from this point over a path about like that. So you see there's this elastic deformation with that slope, and then this would be permanent deformation that you would get that way in a tensile test. So let's consider now, you know, what we had in that little YouTube movie of where we got a bar like this. And I'm just going to put a simple force on it like that and consider the force deflection relationship, where the deflection I'm considering is a change in length in that direction as well. Okay. Bear with me, it will make sense in a minute. I can imagine it may not right now. Okay, so here's elastic deformation. Again, the idea here is we have a simple bar. We're going to pull on it this way. Okay, so as I take that bar and I pull on it, I think all of you, particularly those of you who are chemistry teachers, the idea that you are very comfortable with the idea you've got some kind of an equilibrium bond length. As you put a force on that, you could stretch those interatomic bonds, and that's indeed exactly what's happening during elastic deformation. You put a force on, you cause these bonds to stretch slightly, you remove the load, and those bonds snap back. So this is my force displacement curve, and for something that is linear elastic, means that the slope, the behavior between force and elongation is linear. Elastic means it returns back through zero. You get something like this, and this is typically what we see metals and ceramics. You can do something very, very similar with a rubber band, and it's not really bond stretching that happens. It's a little more complicated. It's for those of you who are chemistry geeks or physical chemistry geeks, it's really configurational entropy is what's going on. You get this nonlinear elastic behavior. And again, nonlinear means that it doesn't follow a line, and elastic means that it's reversible. Okay. The important point I want you to get right now is that for metals and ceramics, it's this interatomic bond stretching that gives us reversible behavior. And that's a big deal, and we'll find out that plastic behavior works very differently, but this elastic behavior is all based on interatomic bonding, which is, of course, the main domain of chemistry. Okay, so if you take this bar, and again, imagine I'm just pulling on this bar, and I pull on it a lot harder, at some point what's going to happen are you're actually going to sever these bonds, and you're going to have some material slide along each other in such a way that it makes this bar longer and does so in a permanent way. And again, our word for permanent is plastic. So this is elastic and plastic deformation. I've put permanent set in it. And so again, if I load, this will be kind of the loading part, and then I unload, you see I'm getting this permanent deformation in the material. And excuse me, and that's what we're talking about. We're talking about plastic deformation. So the mechanism is different than what we had for elastic deformation. When we did elastic deformation, it was simply bond stretching. Now when we're doing plastic deformation, there's bond stretching and there's actual motion of atoms past one another. That's what we call shearing. And that shearing happens in response to a shear stress. And I'll brush over that briefly, but you'll hopefully get the key ideas there. Okay, so now geometry is a big deal in all of this, and we're not going to have nearly enough time to get into how to do this in great depth. And there is great depth. This can be done. It's a fascinating field, and it's really is a part of a subdiscipline of partly materials and partly mechanical engineering that get into all this. But let's now just imagine I've got a load, 50 kilograms, or always like to say in the United States, about 100 pounds, and put it through a thin cotton thread that can cause that thing to fail. I could also increase the cross section, turn it into, take a whole bunch of threads, turn that into a rope, and that can hold that 100 pounds very, very easily. Okay, so that just shows that shape and size matter. Nothing that we don't already know already, right? Okay, so let's be quantitative about that. And the thing that we've changed with that is both materials might fail at about the same stress. So stress is really this kind of an intensive property that we can use that determines what goes on. And so we like to speak in terms of stress and strain, because stress and strain are really geometry independent, whereas force depends on what force does depends on the geometry of the system. So engineering stress, going back to this, pull on this. The important thing we're doing is we're putting a force in that direction on this thing, and the area that this breaks over would be this area normal to that plane. So we've got a plane defined by the same direction force is on. It's that area normal to that matters. There we've got a small area. Here we've got a big area normal to that. So normal stress is basically the stress perpendicular to the plane, So this would be the force. This would be, again, might have that mass that's pulling in that direction. The normal stress is stress normal is equal to force over this area that's perpendicular to that, and we usually give that the Greek symbol sigma is what goes with that. Okay. Turns out, even in something where you're putting a normal stress on, you can find shear stresses. I'm not going to, maybe I will talk about that a little bit. So if I'm pulling something like this, turns out if I draw my coordinates like that, and don't worry too much about this, there's shear stresses that act like that on the body as well. And we can get into the stress analysis, but the important thing is we can also define a shear stress. A shear stress is given the Greek letter tau. Tau, again, is simply force over area, but now the force is going this way. And again, this plane that we're interested in is really parallel to that force direction, so we're really worried about that area that's parallel to that. Okay, and that's what a shear stress looks like. Again, if you're going to get into math and units, there's a great all kinds of things you can do with this in terms of factor label method and keeping units right. Stress, either way, has units of force over area or force over length squared would be the other way of putting that. And those are the units that we care about. And then, so here in the US and the UK, we like to use pounds per square inch. Our English units, almost everybody in the rest of the world uses newtons per square meter. Just as a matter of, does anybody know what a newton per square meter is? That's equal to Pascal. And if we take 1,000,000 of those, that's a megapascal. So it turns out 1 Pascal is a really small pressure. And remember, a Newton, and this might be something that, this is one of my favorite science stories, is you know how Newton was apparently sitting under this tree in Cambridge, England. He got hit on the head with an apple back when. And that's sort of where the idea of the force of gravity on an apple being called a Newton came from. And so the 1 Newton, turns out, is about the weight, the force due to gravity on 1 medieval apple. Small apple, that weight is about the force of a Newton. If you take that force and divide that over an entire square meter, you can imagine that's a really small force. That's like 1 apple sliced to where you could spread it out or applesauce it to 1 meter. Squared, and it's a really, really tiny force. So we often deal with things in megapascals and gigapascals. 10 to the million apples per square meter or a billion apples per square meter are often the units that we like to use. Anyway, good stuff for math in there as well. We can do strain as well. And again, this is something that stress and strain are things that appear in the ASM camp. Longitudinal strain, in this case, if you take a bar like this of some original, this is my original length, pull on it like that. Longitudinal strain, we give epsilon, is basically, delta L over L. So this would be, actually keep with the same nomenclature used in the slides, change in length divided by initial length. And then it turns out there can also be a little bit of a lateral strain where things move in sideways, and let's not worry about that right now. And then the other thing we can do is we could also see that if you shear something, if you start out with something that's drawn on to this as a square, in that orientation, after this deforms, what's going to happen is that it'll distort to a shape exaggerated like that. It'll get longer in this direction. So this is really the tension direction. And also turn that into a shear strain. It turns out there's a shear stress if you do the math right. And that's also shown by this angle of distortion. I think that's something you're not going to get into with your students. Let's not worry about that too much. But this is probably pretty important, is understanding how axial strain works. So again, let's get back to reversible deformation. Now we can put numbers behind it. Again, this is my initial shape. Put a small stress on it. We stretch these bonds in this direction. We unload, we go back. And now we can put a number on this, and we can say that the elastic modulus is equal to stress over strain, and that would indeed be the slope of this thing. And we can use that to compare one material to another. And indeed, elastic modulus is something we use in mechanical design all the time. Elastic modulus and strength, elastic modulus and shape determine how stiff a material is going, or a shape made out of material is going to behave. So if you make an I-beam out of aluminum versus steel, you know what that shape is, you know what the material is, you can figure out what the stiffness of that beam will be in bending very accurately. And it turns out the more you make things, or the more you can move the material out to the outsides like you do in an I-beam, the stiffer that is at a given amount of material. And so we like to do those tricks all the time. We make beams and hollow tubes and all that. It gives us great mechanical advantage. So here's our linear elastic properties. Again, this is your elastic modulus that can go, this is tension over here, this is compression over here. And then also, as the material elongates this way, it tends to suck in that way. That's governed by Poisson's ratio. Let's not worry about that right now. Just let's focus on elastic stiffness. So the higher the modulus, the stiffer the material is. Just as a matter of just putting some numbers on it, the elastic modulus of iron, for example, it's about 30 million pounds per square inch, which is equal to about 210 gigapascals. And again, you'd work through the units. Stress has units of force per area. Strain has units that are dimensionless, so that's why we have, again, stress units in here. Again, a modulus of aluminum is about 1/3 of that of steel, about 10 million psi, which is equal to about 70 gigapascals. Okay, let's continue forward. So again, properties from bonding. Again, what this really has to do with, for those of you who are chem teachers, again, this is very much directly related to interatomic bonding, and you've probably seen plots of potential energy versus interatomic distance. This is really the bonding energy. Radius is about the radius, and for most metals, the interatomic spacing is about 2.5 angstroms, so the radius would be something like 1.75 or so angstroms, or 1.25 angstroms. It's about your average radius, and since that's about the same, it turns out it's this curvature that matters. So the stronger your bonding is, typically the higher your modulus is. So that tells you that things like tungsten, you expect to be very, very stiff because they have very high bond energies, and indeed they are. Aluminum is not so stiff. Graphite has very, very high bond energies. So does diamond. That makes for those being materials that have also very good elastic stiffness, very high elastic stiffness, because it all comes back to this bonding. We could be quantitative about that, but in this course we're not going to. So again, here's a plot. Again, one of my favorites, logarithmic scale, going from very low, 10 times greater, 10 times greater, 10 times greater, up the way. Some of our toughest or stiffest materials are things like tungsten. Those with lower bonding energy, magnesium, are much lower. Polymers are generally much lower. Basically, this is because, we'll talk about polymers a little bit later, you can have covalent bonding along the chains, which are very, very strong bonds, but these chains are usually held together by secondary van der Waals bonds. As a result of that, you don't see great stiffness. Ceramics, ionic, and covalent bonds are very strong. Again, you see very high stiffness. Composites are somewhere between these things because they often engage a lot of polymers in them. You don't see quite as high a stiffness. But again, what's incredible here, you're seeing engineering materials going from this to this, so you're going over about 1, 2, 3, 4, 5, 6 orders of magnitude. So you're seeing huge changes in what you can get. So materials down here are very, very floppy. Materials up here are very, very stiff. Floppy materials are very often very good for biomaterials, where you want the compliance to maybe match skin or some kind of gooey tissue. And up here, if you want to build a bridge or something that's really structural, you don't want it to deform. Metals and ceramics are really, really good. Huge range. So measuring moduli in ceramics, we typically do this in 3-point bending rather than in tension. Partly a lot of this has to do with the idea that it's very difficult to take these tensile bars. If you make something like this, cut a bar, might be axisymmetric or flat. You can take that, pull on it. It's hard to do the alignment very carefully with which you need for brittle materials, but it's much easier to do it in 3-point bending. So again, 3-point bending is a good way to measure stiffness and strength of brittle materials. Again, we're not going to go through this in too much depth here. Again, plastic deformation, again, we typically do by a tension test. Again, we can load this up. Initially, this is the elastic regime. You see this bending over typically once the atoms start to shear past one another. And then if you unload, the elastic stretching is gone, but you see this permanent deformation, and you get this plastic deformation. And this here, from here to here, this would be that'd be your elastic deformation. Okay. So again, this is what we would see. This is a little bit less cartoony, but about the same sort of thing. Usually these elastic slopes, this is your elastic modulus. The elastic slope is much, much higher than these plastic slopes, and you see the real abrupt turnover there. And again, this strain here is provided by atoms sliding past one another. This strain here is provided by atoms stretching. And this elastic strain is usually less than about 0.5% or so in metals. It can't be very big because things will start to break or deform otherwise. This is sort of typical. There's some other examples where you can break that, but those aren't typical examples. So one of the things that we define very carefully and use as a standard in engineering all the time is something called the yield strength. And just to make it so we can have an agreement on, the yield strength generally is the stress at which noticeable plastic deformation takes place. Just to make it so that most labs can do this in an easy way and we can have an agreement on what that means, we make a definition that the yield strength is where we see about 0.2% plastic or permanent deformation. And that's our definition of yield strength, and we can measure that like that. What we also see in materials is, and this is something we go through quite a bit in the ASM camp, is that the idea that as you deform materials, or metals in particular, they almost always get harder. So if you were to do a tensile test, just the same way you saw in that YouTube video or we've talked about, you can see that materials get harder, and again, stress is equal to force. Stress is equal to force over area. So the force required to keep forming this material increases. This is strain on this axis. This one has small hardening. This has large hardening. And it turns out materials with a lot of hardening turn out to be materials you can stretch a long way. And we like to have these high strain hardening exponents. We try to put this into a mathematical form. This is a common empirical mathematical form. By empirical, I mean there's no reason it has to be that way. It's just some guys said, hey, this equation fits pretty well, and by golly, it does. And so we can model this way, and this n is something we call the strain hardening exponent. And generally, more formable materials have higher strain hardening exponents associated with them. By formability, I'll talk about forming in a second, I think, a little bit more depth. Actually, let me go back and talk about this. So forming has to do with how far you can stretch something. And if we think about the way an automobile is made, for example, you end up with a piece of steel that's rolled. Looks something like a good old Reynolds wrap you might pull out of the drawer. And then you take that and you put it between some hardened steel pieces that have the shape of the fender you want to make, and you basically impose that shape onto it. And the material has to stretch a lot to do that. And it has to stretch without failing, and it turns out these hardening properties have a lot to do with that, and that's what I mean by formability. That kind of gets into what we're going to talk about later when we talk about how this all works with automotive design. Tensile strength is the other important property, and basically tensile strength is basically the the tensile strength is basically the maximum force divided by the original cross-sectional area. And so this is the tensile strength, so this is force over original area is engineering stress, so that becomes a tensile strength. That's the highest. So if you know what the cross-sectional area is, you know what your tensile strength is, you can calculate what the highest possible load that component could carry in tension is before it ends up breaking. And in metals, this is usually where noticeable necking starts. In ceramics, it's where crack propagation starts. And in polymers, it's where you start breaking these individual covalent chains. We can also measure the strength of ceramics. Basically take the same sort of arrangement, measure force, measure midpoint deflection. We can calculate the stress that exists at this point where a crack starts to come in. And you can see just cracks all at once, and that represents a tensile strength of the ceramic. So we look at tensile strengths. Metals, again, are usually the winners. We can make some steels and titanium alloys that are very, very strong. Composites can also be very strong. Ceramics, the key to strength is actually minimizing the flaw size because they fail and fracture. And if you've got large cracks, that will cause them to fail more quickly. Polymers generally do not have very high strengths, so what we do is we do things like mix them with carbon fibers in order to get high strength, and that's how we go from polymers to composites if we really want strength out of them. Hardness is basically a resistance to permanent deformation of the surface, and this is a quick test that tells you about how strong a material is going to be in tension. And basically what we do is we take a very hard, like a hard steel ball or a diamond, we apply a known force, measure the size of the indent, and basically the hardness is again related to force over area. And plastics are very soft, diamond is very hard, things are in between, and this is a simple way that we can measure that, and I don't really want to say too much more than that. But again, there are ways. There's something called I think Mohs hardness scale, where you can see what material will scratch what material, and it turns out materials that are harder material will scratch a softer material. Diamond will scratch copper. Copper will scratch chalk, but not vice versa. So you can actually rank materials that way too, and that's also a measure of how easily things are indented. And you can use that as another simple measure of hardness, even in a classroom environment with very little money. Ductility is really important. Again, if you're going to do metal forming, make something like an automotive fender. Ductility is basically how far does something stretch before it fails. So elongation is change in length divided by initial length. And this is something that is fairly brittle. You see there's very little permanent deformation before failure. This is something that's very ductile. You see a lot of permanent deformation before failure. And if it's stretching a long way, metals also retain their volume. So if it's stretching this way, it's moving in that way. And it's basically, ductility is a good way to tell you something has good ductility. That means you can probably shape it very easily. You can take it and use hardened dies and shape it into the shape you care about, mold it into a shape you care about. And it's a very, very common way we do manufacturing. If you go back and look at any manufacturing videos, you'll see we do all kinds of things by forcing the material into a shape we like. And high ductility means it's going to go along for the ride rather than fracture. Big idea in materials manufacturing. And then toughness is basically the energy to break something. And it's really, if you're doing, I want to do math on this, it's really the integral under these curves. Ceramics typically have very little toughness. You can drop them and they'll fail. That's because there's no ductility in them. The energy to break something is this basically related to this integral, and that has to do with fracture. And if you have something with a crack in it, you've got very high stress in front of that crack. If you pull this way, and if something is very tough, that's going to cause deformation in this region and cause the material to flow. It'll take a lot of energy to do that. Whereas if something is very brittle, like a piece of glass, you've all seen, and the crack will just run across the material and cause it to fail with very little energy expended. So in this lecture, we don't have enough time to do fracture mechanics any justice whatsoever, but I do want you to recognize that it's a different mode of failure than either elastic or plastic deformation. It has its own quantitative framework associated with it, and materials that can plastically deform easily are generally very tough. And that's about all I'm going to say about that. So here's, in summary, stress and strain are two things we like to use. We use those because they're size-independent measures of mechanical properties. Elastic means that things are reversible. Plastic means deformation is permanent. Ductility is a plastic strain you get at failure. Toughness is the energy required to break material. Things like steels and titanium alloys are generally very tough, whereas glasses and ceramics are generally very brittle, which is the opposite of tough. And there are many possible definitions of strength, and we have to make sure we're talking about the same language. Stiffness is resistance to being floppy. Strength is resistance to permanent set. Things might rupture over time at high temperature beyond this course. Strength at fracture can be important. Energy absorbed at fracture can also be important. These are all alternate definitions of whether something is suitable for the right kind of mechanical loading. So if you're designing an airplane or a car or a seat somebody might sit in during a crash or something, all of these measures can indeed be important in design, and they are things I think that can be kind of accessible also. We all